using Pythagorean's theorem, we can find an expression for the distance between the 2 points. So we'll call the change in the x-coordinate delta x and the change in the y-coordinate delta y. And using Pythagorean's theorem, we get that the distance d equals the square root of delta x squared plus delta y squared. And let's say our 2 coordinates are at x1 comma y1 and x2 comma y2. Then we have that delta x equals x2 minus x1 and delta y equals y2 minus y1. So this gives us our formula for the distance between 2 points, the square root of x2 minus x1 squared plus y2 minus y1 squared. And the order of which you label the points doesn't matter. So if you were to switch like x1, y1 with x2, y2, it'd be the same since you're squaring it. So the negatives wouldn't matter anyways. So next we have the distance between a point and a line. So when we say the distance from a point to a line, we mean the shortest distance it takes to travel from the point to the line. So we can see that if we're traveling from a point to a line, that means the shortest possible path is one that is perpendicular to the original line. Because if the line isn't perpendicular, it would form a right triangle with the perpendicular path, meaning that it's not as short as the perpendicular path. So the formula is pretty lengthy. It mainly relies on Pythagorean's theorem, as well as the fact that the slope of a perpendicular line is 1 over the original slope. You can probably find the proof somewhere online. We're not really going to go over it. It's pretty lengthy and a bit messy. So the formula you get is the distance between a point h comma k to a line in standard form ax plus by plus c equals 0 is the absolute value of ah plus bk plus c over the square root of a squared plus b squared. And a common way to remember this is in the numerator you have AH, BK, and C, which stands for Burger King calories, because Burger King's not really healthy. And that's just like an easy way to remember what variables go where. And in the denominator, it's just a Pythagorean theorem based on the coefficients of the line. So next we're going to go into the Shoelace theorem. So this is a pretty big topic, especially in competition math. It comes up a lot in like math counts as well as like higher level competitions such as AMC 10s or AMEs and so on. So let's say you had a shape or a quadrilateral with points at 1, 1, 2, 3, 4, 6, and 5, 2. So here you can see our quadrilateral if we drew it. And this is a pretty weird shape. It's not really a square or a rectangle. We can't use base times height. So then how would we try to find the area of this? Well, there's a theorem called the Shoelace Theorem, which I just mentioned, that allows us to find the area of any convex polygon in a coordinate plane with vertices at any point. So here, if you write down the coordinates of the vertices in order, in vertically, you see that we have 1, 1, and then we have 2, 3, then 4, 6, and 5, 2. And make sure that when you're writing out the coordinates, they're in order of how they appear on the polygon. Otherwise, this won't work. So to use the Shoelace theorem, what we do first is we take the first coordinate of the first pair, so 1, and we multiply with the second coordinate of the second pair. So that's our first product. And then we add to that the first coordinate of the second pair times the second coordinate of the third pair, so 2 times 6. And we continue this, so we get 4 times 2, and then finally 5 times 1. So if we drew the pairings on our list, they would show up as diagonals going to down and to the right. So next, from that, we'll subtract 1 times 2, so the second coordinate of the first pair and the first coordinate of the second pair. And we can see that this pairing is like the exact opposite of what we did in the first place. It goes in the opposite direction. So we do the same with 3 and 4. So we have minus 3 times 4, and then minus 6 times 5, and minus 2 times 1. So if you drew all of these out on our list, it kind of looks like a shoelace. So that's why it's called the Shoelace Theorem. And it's also a handy way to remember how to do it. You multiply them like a shoelace. So when we evaluate the sum, we would get 18. 3 plus 12 plus 8 plus 5 minus 2 minus 12 minus 30 minus 2. We would get negative 18. And the area can't be negative. So something that's stated in the Shoelace theorem is that we always take the absolute value. And then after we take the absolute value, we divide by 2. It's based on how it's similar to like the formula of a triangle where you have the base times height divided by 2. And that's about where the formula is derived from. We use triangles. That's why we divide by 2. So we would get the absolute value of negative 18 is 18, and then we divide by 2 to get 9. So a general formula of this would be 1/2 times the absolute value of the first x-coordinate, the first coordinate, the x-coordinate of the first pair, and the y-coordinate of the second pair, and so on. So the absolute value of x1, y2, plus x2, y3, ... plus xn, y1, where xn is the last x-coordinate. And then from that, we subtract the opposite pairing. So y1, x2 minus y2, x3 minus ... all the way to yn, x1, where yn is the last y-coordinate. So why don't we try this in another example problem?
Okay, so the problem is about just finding the area of a random triangle with the coordinates as given, p, q, and r. So in this problem, we could draw them out. P is at -2, 1. Q is at 3, 8. And r is at 9, 3. So if you didn't know the Shoelace theorem, you could obviously try working it out by drawing in right triangles and splitting it up. But as we know the Shoelace theorem, we can pretty easily just split it up. So again, listing out the coordinates vertically. And one common way is just to list out the last one, the first coordinate again at the end, so you don't forget to multiply by it. So the first sum will be -16 plus 9 plus 9 minus 2. Or sorry, plus 9 plus 9. While the second sum would be -3 minus 72 and then plus 6. So if we add these all together, this comes out to 67. And then again, we have to remember, the absolute value of this comes out to 67. And we should remember to divide by 2 at the end. So our answer comes out to 67 over 2, or 33.5, as we want it as a decimal. Another common concept in coordinates are transformations, which are basically ways to move around coordinates, and the main ways to do so are translations, reflections, rotations, and dilations. So a translation is the easiest of them all, and simply involves shifting every point of a function as if you were sliding it. So for example, if we want to shift a function a units to the right, like let's say we have a random line going through x equals 2, we'd replace every instance of x with x minus a. That would cause this function to shift a units to the right. Similarly, if we want to shift the function up by b units, we'd replace every instance of y with y minus b. So for example, if we had the function y equals x plus 2, if we had the function y equals x plus 2, and we want to shift it 2 units up, we would get y minus 2 equals x plus 2, so y equals x plus 4. And this would shift the overall function up 2 units. And similarly, if we want to shift 2 units to the right, we do y equals x minus 2 plus 2, y equals x, and this would shift the function 2 units to the left. Reflection is the next major transformation and involves taking a mirror image about a line. So most reflections occur about an axis, like the vertical or horizontal. the x and y axis, but they can also take place over a vertical or horizontal line or any line in general. The main principle is that the line connecting the point and its reflection are perpendicular. So for example, if I took the point 3, 4 and reflected it across the x-axis, it would show up at 3, -4. And we can basically derive a general formula for most of these common reflections across the x-axis, y-axis, and the lines x equals y. Specifically, if we reflect across the x-axis, the x-coordinate remains constant, but the y-coordinate is reflected, so it goes from x, y to x, -y. Similarly, for the y-axis, we go from x, y to -x, y. And finally, the third kind of common rotation is across the line y equals x. And for example, if we rotated the same point 3, 4, we'd get 4, 3. And in general, this formula turns x, y into y, x. And the third kind of transformation that we use is rotations, which are, as the name suggests, simply rotating around a given point. And this can get fairly complicated for an arbitrary rotation, so we'll focus on just quarter turns. So the angles are typically defined for rotations in the counterclockwise direction, and we could play around a bit to find each of the formulas, but for today's lecture, we'll just give you the formulas. So if we rotated 90 degrees counterclockwise, x, y would turn into negative y, x. 180 degrees counterclockwise or clockwise are the same thing, would turn into negative x, negative y. And then finally, 270 degrees counterclockwise would be y, negative x. An interesting property of this is all of these can be derived from just reflections, as this 90 degrees counterclockwise is simply a reflection across the line x equals y and then across the x-axis, and exactly the opposite for 270 degrees. And for example, if we want to show it visually, the point 4, 3, if we rotated 90 degrees, would simply mean that we go the angle formed between the point and the rotation is exactly 90 degrees. So if we rotated 4, 3, 90 degrees, we get negative 3, 4 as our new point. The final type of transformation is the most complicated in a way, and it's called a dilation. It involves a central point and then essentially stretches and compresses all the distances around it to everything else. So the easiest way to consider it is a dilation around the origin. So if we have some random point x, y, and we dilate things around the origin with a scale factor of 2, that means that every point x, y will double the distance away from the origin and will become 2x, 2y. So in general, a dilation across the plane with the dilation around the origin with a scale factor of k turns x, y into kx, ky. But we can also extend this to a general point of dilation by translating the point that so for example, if we want to dilate around some point a, b. So first we translate the overall coordinate plane back to the origin. So if we have x and y, we'll start by shifting every point such that a, b appears to be the origin. So a is subtracted from x, b is subtracted from y. Then we dilate as if we're at the origin, which will multiply everything by k. And then finally, we have to shift back to our original coordinate system. So we'll add a again. And this is the formula for a general dilation around the point a, b for any point on the grid x, y. So now we'll go over an example question about that.
All right, so this is from Math Counts Countdown. So as you know, most countdown questions are about being fast. So we have a segment with endpoints at g, which is -2, 3, and h, which is 4, 7. And the problem tells us that it is dilated by a scale factor of 2/3 with a center of dilation of 0, 0. And it asks us, what is the sum of the coordinates of the new points? So we know that when we're dilating about 0, 0, since it's 0, 0, we're basically just multiplying all the coordinates by 2/3. So since this is a countdown, we should try to find the fastest way to do this. So instead of individually multiplying each coordinate by 2/3, what we can do first is we can sum all of them up. So we have -2 plus 3 plus 4 plus 7, which is 12, and multiply by 2/3 to get 8, which is what this I got. So yeah, so this shows us how doing things the right way can make you much faster than if you were to individually multiply them out. And it's a really important part about math cans to do problems as quick as you can. So now we'll go into a few more problems that are rather easier on reinforcing some of our basic ideas. And after that, we'll get into some more difficult competition problems that require like a more difficult application of like shoelace or transformations and whatnot. So here's problem 1. So we have the coordinates of a vertices of a trapezoid that are at 1, 7, 1, 11, 8, 4, and 4, 4. So if we draw in those points, we see that, oh, this one's a bit out of the graph, but here we are. We have that the trapezoid looks like this. So using what we already know about trapezoids, what we could do is evaluate what the two bases are and what the height is and use our formula. But that would require a lot of time and a lot of work. And we want to be as fast and as efficient as possible. So we kind of think, instead of doing it the normal way, we can just use shoelace. It'll be much faster, right? And it's easier. So when we use shoelace, we do shoelace. We have 1, 7 here, 1, 11, 8, 4, and 4, 4. Multiplying out, it becomes 11 plus 4 plus 8 times 4, which is 32, plus 4 times 7, which is 28. And from that, we subtract 7 times 1, which is 7, 11 times 8, 88, 4 times 4 is 16, and then 4 times 1, which is 4. So this becomes negative 40. Since we're using shoelace, we take the absolute value, it becomes 40, and we divide by 2 to get 20. And that's our final answer. And you can see doing it this way would be a lot faster than if we were to find that the two bases were of length 3 root 2 and 7 root 2, and then find what the height was and then plug in the formula.
Okay, so our next question is somewhat similar. It's asking to find what would the area be in square units of a triangle with these 3 vertices. So what do you guys think the easiest way to do this would be? So some people might commonly think it's shoelace, depending on as we've done shoelace for the previous 3. But if we actually draw out the points, we'd see that they form a much easier shape to do so we don't actually need shoelace. So 4, -1 comes here. 10, 3 is over here. And 4, 5 is over here. So we can notice that this is actually an easy triangle which we can use. As the base is simple, we can easily see the area of the length of the base is 6, and the height of the triangle is also 6. So we don't actually need to use shoelace, and we can simply do that area equals 6 times 6 divided by 2 equals 18. So this is another example of how so you always want to find the fastest way possible. So while shoelace is helpful in certain occasions, there are other occasions where it's a lot easier just to look at the shape itself and just calculate it manually. Shoelace in general involves a lot of multiplication and can cause silly mistakes. So if you see an easier way, you should take it.
All right, so our next question, we have parallelogram ABCD, and we have A at 0, 1, B at 2, 1, and C at 4, 0. So as some of you guys realize, this is not the most difficult problem, but it kind of highlights something special about parallelograms, where we know that AB is the same as DC. It's just like translated. So when we translate B to C, it's a translation of 4 minus 2 and 0 minus 1, so 2 minus 1. So we apply the same transformation to A, and this gives us getting D is at 2, 0. And we can tell that pretty clearly from the graph. But without looking at the graph, you can just do it in your head without having to draw it out. And this gives us our final answer of 2. So here we have another pretty easy problem, but it just highlights a basic concept that you should know. So we have a line that passes through 2, -5 and -1, 8. So it asks us for the slope of the line that is perpendicular to K. So first we find the slope of K. So we know that the slope of K, which we'll call M, we have M equals 8 minus -5 over -1 minus 3, or -1 minus 2. So this gives us a slope of -13 over 3. And as some of you guys realize, the answer would be 3 over 13. Because when we are finding the slope of a perpendicular line, let's say the original slope we have here is M, then the slope of the perpendicular line would be -1 over M. And this applies to all lines. And plugging this in, we get 3 over 13.
All right, so our next problem is a lot more competition oriented and isn't as easy as the previous few. So this problem is basically asking if x and y are integers such that x minus 3 squared plus y plus 4 squared equals 25, what's the greatest possible value of x squared plus y squared? So as you guys should have known from the handout, something of the form x minus a squared plus y minus b squared is a circle. And this specifically is a circle centered at 3, -4 as shown in the diagram over here. And the other thing to notice about this problem is that x squared plus y squared looks very familiar to something we've covered before in this lecture, specifically the distance formula. If you notice, when we use the distance formula, we have d equals delta x squared plus delta y squared. So x squared plus y squared is simply the distance of a point in the circle away from the origin. Since if we let if we let one of the coordinates be 0, 0, the other coordinate be x, y, the distance simply equals x squared plus y squared. And now, if we want the greatest possible value of x squared plus y squared, that's essentially the same thing as finding the greatest possible value of a distance, since it's directly proportional to each other. So even then, this problem might appear hard at the first glance because we aren't exactly sure how to find the farthest point. But if we look closer at the graph, on an actual problem, you won't be provided with the graph, but you'll have to sketch it. If we look closer at the graph, we'll notice that this is a circle with radius 5, as the equation equals 5 squared. And it's centered at 3, 4, which means that the distance from the origin to the center of the circle is 5 units. That means that the origin is also on a point on the circle. So the unit farthest away from the unit farthest away from the origin is diametrically across the circle, which would be over here. So that would mean that distance equals 10, since the radius is 5, which means the diameter is 2. But that's if we said the answer is 10, we'd be making a common mistake. The question is actually asking for x squared plus y squared, which is distance squared. So distance squared equals 10 squared equals 100, which would be our final answer for this question.
All right, so our next question involves, so the question states that we want to find a point x, y on our line here, which is x plus y equals 3. And it is equidistant from the 2 points 3, -1 and 7, -9, which we've labeled as A and B respectively here. So this seems pretty difficult at first, not really sure how this applies to coordinate geometry. But if you recall from some basic geometry, the points that are equidistant from 2 endpoints of a line segment are the same as the perpendicular bisector of that line segment. So if we were to draw the perpendicular bisector of this line, well, since we know it's perpendicular, that means we can apply our formula for perpendicular slope. So we can find the slope of our line segment AB first, which would be -1 minus -9, or -9 minus -1, whichever you choose to do first. And that would be over 7 minus 3. And this comes out to give us a slope of -2. So plugging in our formula, we know that the slope of the perpendicular line is 1/2. And we know that this line passes through the midpoint of our line segment, which would be 5, -5, because it's a perpendicular bisector. So then we can apply the point slope formula to solve for the equation of the line. So this would give us y minus -5 equals 1/2 parentheses x minus 5. And this becomes y equals 1/2 x minus 15/2 x. And we want to solve for the intersection of this line and the equation x plus y equals 3. So plugging in y equals 1/2 minus 15/2, we get that this equals 3/2 x minus 15/2 equals 3, which gives us 3/2 x equals 21/2. So solving for x, we get x equals 7. And plugging back in to solve for y, we get that y equals -4. So that gives us our final answer. Our point is 7, -4. All right. So here we have a question that primarily asks us about transformations. And it gives us a bunch of transformations in a row. So the important part about this is to keep track of where your points are. So it helps to draw out your points step by step. So here we have point A is at 5, 9. So up here. And we have two different sets of transformations, one by Terence and one by Poe, as we can see. So let's go through Terence first. So we have Terence takes a point A and rotates it clockwise 90 degrees about origin. So using our formula for 90-degree rotations, rotating it clockwise 90 degrees is the same as rotating it 270 degrees counterclockwise. And using that formula, we get is equal to y comma -x. So that means our new point would be at 9, -5. Then it tells us that we move it 1 unit down and 1 unit to the left. So this means we subtract 1 unit from the y coordinate and subtract 1 unit from the x coordinate. So this moves it to 8, -6, as you can see here. And then it tells us that it gets dilated by a factor of 1/2 about origin. So we just multiply all the coordinates by 1/2, and this gives us 4, -3. And then finally, what Terence does is he reflects it across the y-axis. So since it's the y-axis, we just change the signs of the x value. So this gives us -4, -3. So this is our first set of transformations. Now, it asks us the distance from this point B to another point C, which is what Poe gets. So what Poe gets is that he takes A that we had in the beginning, and he reflects it across the y-axis first. So we change the sign of the x-coordinate, so we get -5, 9. And then he rotates it 180 degrees about origin. The direction doesn't matter since 180 degrees either way is the same. So this just gives us -x, -y. So the point -5, 9 goes to 5, -9. So now what Poe does is that he translates it left 4 units and up 6 units. So we move left 4 units, we get the new x coordinate is 1, since we have 5 and -4 is 1. And when we move it up 6 units, we have -9 plus 6. So it moves to 1, -3. And now what Poe does is he dilates it by a factor of 1/3 about the point 1, 0. So using our formula for dilations, we have that our new point would be, since we had our dilating point is 1, -3, it would be 1/3 times 1 minus 1 plus 1, comma, 1/3, -3 minus 0, plus 0. So this gives us our new point 1, -1. And this is our point C. So now to find the distance, we just use our distance formula. So we see that the change in x is 5, since we go from -4 to 1. And the change in y is 2, since we go from -3 to -1. So this becomes 5 squared plus 2 squared, which is square root of 29. And that's our final answer.
Okay, so our next problem is again dealing with the circle, but this time we're looking at a different property. So we want to find the largest value of y over x for pairs of real numbers that satisfy the equation x minus 3 squared plus y minus 3 squared equals 6. So does anyone notice anything about what y divided by x looks like? Yeah, exactly. As James said, y over x seems similar to the formula for a slope, specifically the slope of a point going through the origin and on the circle. So this problem is basically asking us what is the steepest line through the origin that touches a point on the circle. And we'll notice that this happens when the line is exactly tangent to the circle. As if it were anywhere slightly more inside, like such as here, we could simply move it slightly more to the left and we'd get a steeper line. So one interesting property of tangents is that it's always perpendicular to the radius. In case you haven't learned that yet, we'll cover that more in a future lecture about circles. But that means we can use that the radius, the line connecting C to B, which is the radius, we can use the fact that its slope is a negative reciprocal of the slope of y over x. So more specifically, we get that the slope of the tangent line, y over x, is equal to negative 1 over the slope of the line from the radius to the tangent, which is y minus 3 divided by x minus 3, if this point is x comma y. Simplifying this a bit, we get that y times y minus 3 equals negative x times x minus 3. And if we rearrange this, we get x times x minus 3 plus y times y minus 3 equals 0. At this point, we might notice that this looks a little familiar. More specifically, it looks very close to the original equation of x minus 3 squared plus y minus 3 squared equals 6, which we can rewrite as x minus 3 times x minus 3 plus y minus 3 times y minus 3 equals 6. So we can actually subtract these two equations, which would give us 9 minus 3x plus 9 minus 3y equals 6. And that simplifies our equations a lot, as we can resimplify this to get x plus y equals 4. So now we have a system of equations that we can more easily solve. X plus y equals 4, and x times x minus 3 plus y times y minus 3 equals 0. So at this point, this problem gets a little messy, and that's pretty characteristic of coordinate bashing whenever there's anything other than lines involved. And we'll have to end up using the quadratic formula to solve these equations. So we can substitute in y equals 4 minus x into this equation, which will give us x times x minus 3 plus 4 minus x times 1 minus x equals 0. And if we expand this out, this would give us 2x squared plus 8x plus 4 equals 0. Or x squared plus 4x plus 2 equals 0. Now at this point, this is a particularly messy quadratic since there's no easy way to factor it. So we have to end up just using the quadratic formula to do so. So we cover a bit of the quadratic formula in our handout, but in case you haven't learned it yet, be sure to look it up online, as it's almost essential for a lot of competition math problems. So specifically, we get x equals negative 4 plus or minus the square root of 4 squared minus 4 times 2 all over 2, which if we simplified it out equals 2 plus or minus square root 2. Now, as the problem wants us to maximize y over x, we'll choose the smallest value of x and the largest value of y. Specifically, that would give us x equals 2 minus root 2, and as x and y are symmetric, y would equal 2 plus root 2 then. So the last step is simply just plugging in these values to get our slope. Y divided by x would equal 2 plus root 2 divided by 2 minus root 2. And this isn't a particularly nice expression, so we can try rationalizing the denominator. So if we multiply both the top and bottom by 2 plus root 2, this equation comes out to 3 plus 2 times the square root of 2, which is our final answer.
All right, so All right, so here we have our next question. This is from an AMC 12, so this is a fairly difficult problem. But it's actually pretty easy if you know what to do. And based on everything we've already taught you today, this is actually not too difficult of a problem. So let's tackle this AMC 12 question. The vertices of a quadrilateral lie on the graph of y equals ln x. So ln is the natural log of x. If you need some clarifications on this, it's on handout 0, which is also on our website. So it also tells us that the x-coordinates of the 4 vertices are consecutive positive integers. So it asks us what the area of the, it tells us that the area of the quadrilateral is ln 91 over 90. And it asks us for the x-coordinate of the leftmost vertex, which is telling us to ask for the smallest of the 4 consecutive numbers. So since we're trying to find the coordinate of the leftmost vertex, we'll call that x. So if you look at our graph, we have 4 points of our quadrilateral, x, comma, ln x, since they lie on the graph of y equals ln x. And then x plus 1, comma, ln x plus 1. Then x plus 2, comma, ln x plus 2. And x plus 3, comma, ln x plus 3. So since this is a really weird shape, our first instinct, since this is on a coordinate plane, should be shoelace. And that is like already figuring out half of the problem. So once we figure out how to use shoelace here, if we do our shoelace multiplication, we would get that we have the first pairing, x and ln x plus 1. And then after that, we would have x plus 1 times ln x plus 2. Then x plus 2 times ln x plus 3. Then x plus 3 times ln x. And from this, we will subtract x plus 1 times ln x, then x plus 2 times ln x minus x plus 1, then x plus 3 times ln x plus 2, and finally x times ln x plus 3. So if we want to simplify this, we can combine the like terms. So for the terms with ln x, we see that we have x plus 3 ln x minus x plus 1 ln x. And this becomes 2 ln x. Then for the terms with x plus 1, we have x times ln x plus 1 minus x plus 2 times ln x plus 1. So this becomes negative 2 ln x plus 1. And then doing the same for the next two terms, you get negative 2 ln x plus 2. And then finally, plus 2 ln x plus 3. So we've already covered properties of logarithms on handout 0. If you need a refresher, you can go look at that. But using our properties, we can actually combine the logarithms. Since we know when we subtract 2 logs, it's division within the parentheses. And when we add 2 logs, it's multiplication within parentheses. This becomes 2 times ln x times x plus 3 divided by x plus 1 times x plus 2. So now we have to make sure this satisfies Shoelace theorem. So first we have to divide by 2 since we're using Shoelace. So this becomes ln. And then we have to make sure that this is positive. Now if we expand the insides, we become this becomes x squared plus 3x over x squared plus 3x plus 2. Now since the denominator is 2 more than the numerator, the inside is clearly less than 1. So based on the behavior of logarithms, this is clearly negative. So what we do is we have to take the absolute value of this. And when we do this, we can just flip the inside of the ln. So this just becomes ln of x squared plus 3x plus 2 over x squared plus 3x. Now we know that this equals ln of 91 over 90, since this is given in the problem. So that means that when we can get rid of the ln's, and we just get the 2 insides are equal. And when we cross multiply, this becomes 90x squared plus 270x plus 180 when we multiply the top of the first by 90. And then the other side equals 91 times x squared, so 91x squared, plus 91 times 3x, which is 273x. So this just becomes another quadratic, which is x squared plus 3x minus 180. And you don't have to use quadratic formula for this because you can actually just factor this on your own. And this becomes x minus 15 or x plus 15 times x minus 12. And since ln x is only defined where x is positive, that means from our two roots, one is negative 15 and one is 12, only 12 works. So we get our answer is x equals 12. And we're done with an AMC 12 question. And this is a pretty difficult AMC question too. It was question 17, I believe. And all this really was just like using Shoelace Theorem and then using some properties of logs. So like we can already do like most of the problem just based on what we've learned today.
All right, so our next problem is going to deal with 3D shape, while the previous ones have dealt mainly with 2D. The coordinates can in general be like applied to any amount of dimensions. It just gets more complicated in higher dimensions. So more specifically, this problem asks about a square pyramid with base ABCD of length 3 and altitude AE that's perpendicular to the base, which measures 6 units. Point P lies on BE, 1/3 of the way from B to E, somewhere around here. Point Q lies on DE, again 1/3 of the way up. And finally, point R lies on CE 2/3 of the way up, so somewhere up here. So since it says that P lies in BE 1/3 of the way up, it's the same thing as saying that P is a dilation of E by 1/3 around the point B, which is the same for Q and R. If we use our formula, we get that P equals 2, 0, 2. Again, in these coordinate systems, instead of just x, y, we have x, y, z. So if P is 1/3 of the way up from B to E, we get that P is 2, 0, 2. And similarly, we would get Q equals 0, 2, 2. And finally, R equals 1, 1, 4. But we have an issue. Since we're in 3D coordinates, we can't exactly use the Shoelace theorem since it only applies for a 2D plane. So in this case, we want to actually look at what the triangle is. If we draw this triangle, the easiest way to get a feel of how the triangle is by looking at the distances and the side lengths of each triangle. So we can look at each component individually. And the distance formula just says in 2D how it's x squared plus y squared. In 3D, it's simply adding a delta z squared as well, as it's just applying the Pythagorean theorem again for the third side. So the length of P to Q would be the square root of 2 squared plus another 2 squared plus 0 squared, which equals 2√2. Similarly, for the length of QR, we define that the length is 1 squared plus 1 squared plus 2 squared, which equals square root of 6. And then finally, for PR, we'd find that it's 1 squared plus 1 squared plus 2 squared, again square root of 6. So now that we know that two of the side lengths are equal, we get that, now that we know that two of the side lengths are equal, we can actually draw the triangle, and notice that it's an isosceles triangle, with side lengths √6 the same, and the base has 2√2. So this is a triangle which we can actually find the area of much easier than Shoelace, as if we drop down the perpendicular from the top, we notice that it splits the triangle exactly in half, which means that each of these lengths is just √2 and √2. Yeah, exactly. As James said, the way to find the height now would just be to use Pythagorean theorem. Since we know one of the bases is √2 and the hypotenuse is √6, this thing is just square root of 6 minus 2 equals square root of 4 equals 2, which means that the height of this triangle is just 2. And since we know the base of the triangle and the height, the last step is just simply multiplying it out. 2√2 times 2 divided by 2 equals 2√2 as our final area for that triangle. All right, now we have one more question left.
All right, so here we have ABCD is a square with side length of 28. Rectangle APQR is completely inside square ABCD with AP equals 12 and AR equals 4. Line BQ intersects AD at E and line BQ intersects AB at F. Find the area of triangle CEF. So we can assume that P is on AB, since if we flipped it, it would just be flipping everything over the line y equals x. So that doesn't really matter. So we'll start out by first, we already have a diagram, but if you were actually doing this question and weren't given a diagram, the first thing to do would be to draw one. And after that, you would have to label all the points. So here we have A equals 0, 0, and that would mean that B is 28, 0, since the side length of the square is 28. And then by that same logic, C is 28, 28, and D is 0, 28. And now we have to label P, Q, and R. So we know that AP is 12, and since P is on AB, that means it's also on the x-axis. So that means its coordinates are 12, 0. Doing the same with R, we get R equals 0, 4. And since APQR is a rectangle, that means Q is at 12, 4. So now it asks us for the intersection of BQ and AD and DQ and AB. And this is a telltale sign that we should use a chord bash, since it's asking us to find intersections of lines, which are really easy to find using coordinate geometry. So to find the intersection points, we first have to find the equations of the two lines DQ and BQ. So we'll do BQ first. So BQ passes through the points B and Q. So its slope would be 4 minus 0 over 12 minus 28, which becomes 4 over negative 16, which is negative 1/4. So that's our slope. And since we know it passes through 28, 0, we can use point slope formula. So using point slope formula, we get that y minus 0 equals negative 1/4 parentheses x minus 28, which becomes y equals negative 1/4 x plus 7. So notice how when we did point slope formula, we chose to use point B and not point Q. And this is because point B, one of the coordinates of point B is 0. So this makes it just easier and takes less work. And this goes along with the notion of how we want everything to be as fast and as efficient as possible. So if we do the same with DQ, we get the slope of DQ is 28 minus 4 over 0 minus 12, which becomes 24 over negative 12, which is negative 2. So again, with our idea of keeping everything as simple and efficient as possible, we choose D as our point for point slope, since one of its coordinates is also 0. So this becomes y minus 28 equals negative 2x. And this equation becomes y equals negative 2x plus 28. So now we have the equations of both of our lines. Now we want to solve for their intersections. So we know the intersection along BQ and DA lies on the y-axis. So that means x is 0. So we can just plug in x equals 0 into that formula, and we get that if x is 0, that means y is 7. So our point is 0, 7. Then for our other line, we have it intersects AB, and AB is just the x-axis, so that means y equals 0. And that means we get 0 equals negative 2x plus 28, so 2x equals 28, and solving for that, we get x equals 14. So that means our point is at 14, 0. And now we see how nice this is, because while we could have found out these points using similar triangles, since we have similar triangles of DRQ and QPF and so on, since we have these in terms of coordinates, instead of having to evaluate the area of this weird triangle that we don't really know how, we can just use shoelace since we already have the coordinates of all the points. So setting up shoelace, we have 0, 7, then 14, 0, and finally C is given as 28, 28. So multiplying this out, we get 0 times 0, which is 0, then 14 times 28, which is 392, then 28 times 7, which is 196, minus 7 times 14, which is 98, minus 0 times 28, which is 0, and then 28 times 0, which is also 0. So evaluating this, we get that this is equal to 490. Since this is already positive, we don't have to take the absolute value. And since we're using shoelace, we can't forget to divide by 2. And make sure you drill this into your brain because it's very easy after like doing a long problem, calculating and multiplying everything out, and then just forgetting to divide by 2 at the end. Since you've already done so much work, you think it's all over. So this becomes 245, like Felix said, and that's our final answer. All right, so that's all we have for today. If you guys have any questions or anything about what we talked about today, any of the questions we did or any of the topics, you can feel free to ask us. Homework will be posted right after this meeting.
Actually,